Before we begin, I would like you all to please do me a favor and turn off your Wi-Fi on your phones. If you've ever been to one of our talks before, you will know that we remote into our machines at Morgan Stanley to do live demos, and there will be a lot of them today. I really just don't want your email refresh to mess up my demo. Thank you. Hi, everyone. My name's Gjeta. This is my colleague, Adam. And today, we're going to show you how our team at Morgan Stanley built a build tool that can build over 21 million lines of Scala code in under 2 minutes. Sounds pretty impressive, right? And it is, but it's not actually the star of the show today. We're going to introduce to you the Optimus Cirrus platform. And this is what lies at the heart of OBT, the Optimus build tool. Adam and I are both software engineers working as part of a global team on this platform, Optimus, which is now over a decade in the making, and it's being open sourced as we speak. Optimus is both a compile-time language framework built on top of Scala, and it's a fast and efficient runtime. At compile time, we use something called Scala Async, which is part of the Scala compiler, to transform what looks like synchronous Scala code with a bunch of annotations that we define into an asynchronous representation of that code. And at runtime, this means that our scheduler can run that code asynchronously and in parallel, making maximum use of our CPUs and a big in-memory cache. And it's these two features in particular, the asynchronous execution and the caching, that make Optimus a fast and efficient platform. The ability to perform these optimizations automatically at runtime is underpinned by the idea of referential transparency. A function is referentially transparent if, given the same input, it's guaranteed to give back the same output. It's a relatively simple idea as far as ideas in computing go, but it gives us a number of key benefits. The first is that we can reorder calls to referentially transparent functions, because we know that it doesn't matter when or where we run them, the result will always be the same. And that means that I can run referentially transparent functions asynchronously or in parallel. No matter what thread it runs on, it will always give me the same result. And taking that idea one step further, it means that we can distribute a CPU-heavy computation onto a grid of machines. And just like my referentially transparent function will return some input on my local machine, it's guaranteed, given the same input, to return exactly that same output on some machine somewhere in a grid of machines. Finally, referential transparency gives us the ability to cache the results to our functions without concerns about cache coherency or invalidation. And that's because if I store the result of a referentially transparent function in cache, and then later on I come back and I look up the result from cache using that same input parameter as a cache key, I'm guaranteed that that result in cache by definition is still valid, because the referentially transparent function will only ever return that result. So as long as I fully specify my inputs, I'm guaranteed to get the same output. So that's the theory, but what does it mean in practice for a developer working on the Optimus platform? Well, all we ask of her is 5 extra characters at node and a guarantee of referential transparency. If a developer on our platform annotates her function as at node, she is guaranteeing to the compiler and to the runtime that this is a referentially transparent function. And that lets us do the optimizations that we do at runtime. So she is guaranteeing that the function is guaranteed to return the same output given the same input. Its outputs are fully specified by its inputs, and that's regardless of any external state. And that's it. That's really all we ask. We do not ask her to change the return types of her methods. We don't ask her to wrap them up in monads. We don't ask her to deal with caching or to set up callbacks for any asynchronous execution. We take care of the database connections and the infrastructural concerns of setting up a grid for distribution. And that leaves her free to write the code that she wants to write. And it leaves her free to focus on solving the business problem that she is trying to solve. And today, to demonstrate the power of this platform, we've chosen a business problem that hopefully is familiar to lots of you. How do we build the code that we write in a way that is fast and efficient at scale? Adam is going to set out the challenge, and then we're going to show you how Optimus lies at the heart of the solution.
So we have a core challenge of enabling our developers to be productive. All of the code of the Optimus platform the applications and libraries built on top of it are housed in a single repository that is 21 million lines of code. There's over 1,000 different modules in the project, and at the time we started on the path of implementing a build tool using Optimus. Our full build was taking over an hour, which isn't great as a developer to be productive. So in order to address this, we wanted a build system that was maximally concurrent to make full use of available computational resources, or CPUs, did a minimal amount of work every time we asked it to produce artifacts, and was repeatable. So here, for any given state of the source code, like as of a given commit, we want the same build artifacts every time without any sort of manual intervention. So all of the inputs to the build need to be captured and modeled by the build system so that there's no surprises. Most build systems represent the work they need to do to produce the artifacts as a set of tasks with dependencies between them. In our example, I'm sorry, it's not readable. The colors are different.
We can describe it.
Yes, so the example we'll be using is a set of 4 what we're going to call scopes, which are sets of related source files that are built together that have dependencies, right? Some build systems, modules, or projects. Today we'll be using scopes because that's the terminology in OBT. We have an app scope that depends on a data scope and a model scope, which both in turn depend on an infra scope. So a build system sort of minimally needs to ensure that the infra scope is built before the model and data scope to satisfy that dependency, and in turn that model and data scopes are built before the app scope. It's great if it's able to do the work for models and data in parallel to each other to shorten the critical path. But you'll notice here the work for each scope is like that we need to do all of the work is as a single unit of work here. If we decompose it into smaller pieces, let's just isolate the actual critical path for the dependencies. So for example, we could resolve the dependencies up front and then do the compilation to produce class files and then package those class files. And the critical path here is still the compilation of the source files because that's where the dependency exists. But splitting it has shortened the critical path here and increased the degree of concurrency. It is the case that we can do better by further decomposing compilation into 2 phases, because in the case of Scala, it's possible to build a scope once the scopes we depend on have generated signatures and type information. And so if we split the compilation into 2 larger phases of everything before types and signatures are up through that, and then everything beyond that, we can compress the timeline more and be more concurrent. So now Gjeta will be able to show how we can write some code with a focus on referential transparency that and using add node that we'll be able to achieve these sort of execution characteristics using the Optimus platform.
Okay, this is why I don't like slides. So we're going to switch to an IDE and we're going to write a skeleton build tool together live, almost entirely from scratch. I've pre-written some of the classes that we're going to use to model the inputs and the outputs to the build tool, but we're going to write the core logic together live. And the idea is to show you how Optimus enables a developer to focus on the business problem that they're trying to solve rather than the execution concerns. And this skeleton will achieve... Is that a question? Oh, maybe I can change that. Let's see. Is that better? High contrast. What about... Is that any better? What if I type? Can people see this? Zoom in more. How about now? All right. Okay. So throughout this code demo, we're going to focus on writing referentially transparent code, and that's so that we can allow Optimus to perform the optimizations that we talked about. So to recap, we're going to write the skeleton for our build tool. We're going to achieve both pipelining and caching. Okay, let's get cracking. So first things first, let's talk about the inputs. So as Adam already mentioned, our build tool is going to build a set of scopes, and that's going to be represented by our class scope ID. A scope is just a grouping of code that compiles together and shares the same dependencies. One scope will have one build file that specifies those direct compile time dependencies. And here I've given this a bunch of extra fields, the meta, the bundle, and the module. And this lets me essentially create a namespace for my scope. So I can logically organize my code into maybe the organization and the business unit and then the project. So that's the scope ID. A scope will have some information about how to compile it. And we're going to call that the scope configuration. A scope configuration has a reference to the scope ID that it corresponds to. And it has this list of dependencies that we can read from our OBT file. That's our build file. And this is just the direct dependencies required for compiling this scope. And finally, I've included something called the source version. In real OBT, the source version is a hash of all of the Scala and Java source files in this scope, and also any compiler flags or any other input that may feasibly affect the output of our build for this particular scope. And this is because we're trying to write referentially transparent code. So I need to make sure that any compilation I've done for this scope, given this particular source version, this hash of all the content, is always guaranteed to give me the exact same output because we have referentially transparent builds. So in this demo, if the source version changes, that's simulating a change to the source code, and it means that any artifact we generated previously can now not be reused because our source changed. All right, so that's our inputs. Let's talk about outputs. Adam already introduced the idea that we can have different types of compiler outputs depending on the phase of compilation. So we're going to start off with just a generic trait that represents any output I can get from the compiler. And a piece of output, this artifact is going to contain a scope ID, a reference to the scope that this artifact corresponds to. And it's also going to contain something a bit less obvious called a fingerprint. And a fingerprint in OBT is a complete set of information about about our own scope and our source version, but also our dependencies, all of our transitive dependencies and their source versions. And the fingerprint is what allows us to achieve referentially transparent builds because all of our inputs are encoded here. And I know I said that the artifact is an output, but I'm going to come back to that point in just a second. So let's have a concrete implementation of an artifact. The obvious one is the class file artifact. This is the output, the final output of the compiler. These are the class files that then get bundled up into jars. So our build tool is going to return class file artifacts. But Adam mentioned that we can achieve pipelining by splitting the compiler into two different phases. So the typer phase generates method signatures in Scala, and then everything post-typer does the rest of the compilation. And let's just quickly think about why it's even possible to do that. Let's say that I've got code foo, some method foo, takes an integer I, and it returns an integer. And it's got some complicated implementation that's going to take me a long time to compile. Let's say that foo is in scope A. And now let's say I've got scope B. B depends on A, and some code in B is just going to call foo. It's just going to make a call to foo with some input parameter. I don't need to know about the implementation of foo in order to kick off compiling B. As long as I have that method signature, as long as I know that foo can take an integer and return an integer, I can immediately kick off the compilation of B. So that's what we mean by pipelining. And we're going to represent that intermediate output from the typer phase as a signature artifact. So this is just the method signatures. So both of these types of artifacts are going to be outputs. And I said I'd come back to the fingerprint. So the reason that I include a fingerprint in these artifacts is that although an artifact is an output from some phase of the compiler, it's also an input into the next phase of the compiler. So we need to make sure that the output of those later phases is fully specified by the input that we pass in. So it's by passing this fingerprint, which is the mapping from all of our dependent scopes and our own to the source version that was used to produce this artifact. That's what allows us to have referentially transparent builds, and for each input to the later phases of the compiler to result in the same output. Okay, finally, we're going to wrap up those artifacts into a build result. So this is going to be the output. So let's write our build tool. So I'm going to assume that there's some external helper that can read my build files and generate a mapping for each scope. It's going to give me this scope configuration. I'm not going to do the file reading here, but I am going to call this a config source. And it's just going to be a map for every scope ID that I'm going to build to some configuration that's going to tell me how to build that. So this is the final piece of the puzzle that I need here. All right, so we're ready to write our entry method, build scopes. This is going to take a set of scopes to build. And it's just going to return a build result. And remember, throughout this, I'm writing referentially transparent code. I'm going to focus on solving this business problem. I'm not going to think about execution. So the first thing that build scopes needs to do is pull out the configs for this particular set of scopes that we're building. So we're just going to get that out of the config source map. Then we're going to we're going to get the artifacts, and we're going to do that by calling some method, compile, which I haven't written yet, but I will. And once we have those artifacts, and remember these are going to be class file artifacts because this is our final build result, we're just going to wrap them up into a build result and return that. So build scopes, our input is a set of scopes, our output is a build result. All right, so let's write the compile method. And compile, we've already kind of defined the method signature here. It needs to take this information about how to compile the scope, and it needs to return a class file artifact. And that's because this is the final output of the compiler. But this is where we're going to split up the compilation into two phases. So first, I'm going to get a signature artifact for this particular scope config. And I'm going to do that by passing my config into some signatures method that we are going to write. And then once I've got that, I'm going to produce a class file artifact by calling some method classes. And classes is going to be very similar, but it's representing the post-typer phase. So this is the second phase of the compiler. So we're going to take the config, and we're also going to take that signature artifact that we just produced. And then once that's done, we can just return that class file artifact right here. All right, so let's write signatures and classes. So my signatures method only needs one input, and that's this config. And it's going to return a signature artifact, because remember, this is representing the typer phase. And the very first thing that both signatures and classes are going to need to do is fully resolve dependencies. And we're going to do that in a different method, dependencies, which is also going to rely on this config. So dependencies is going to need to actually do the recursion. So at some point, maybe you predicted there's a recursion coming, because although in our example, app directly depends on model and on data, it also has a transitive dependency through those to infra. So dependencies is where we're going to do that recursion. And in fact, I'm going to write another class to represent these resolved dependencies, because they are distinct from the flat list of dependencies that we already have as part of our scope config. So let's create another class, dependencies. And the dependencies is just going to take all of the signatures of our dependencies, because we only need those. So that's just some list of signature artifacts. And it also will need a fingerprint. Just like we said before, this is to allow me to do referentially transparent builds. So that's going to be a mapping from every scope ID that was part of our resolved dependencies to an integer which represents the source code version for that dependency. All right, so let's write the dependencies method. So first of all, dependencies is going to pull out the configs for all of the dependencies that I directly depend on. So let's pull that out of our config source map. So this gives me a bunch of scope configurations for all of my direct dependencies in this scope. Once I've got those, I can get signatures, and this is where we recurse. So now for each of those scope configurations, I'm just going to map this signatures function, and that's going to give me back signatures. And then finally, I need a fingerprint, and this fingerprint is going to represent all of the information about all the input that went into these dependencies. So luckily, my artifact already contains a fingerprint. So I'm going to take all of my dependent signatures and just flat map and get the fingerprint from those. And then finally, I can just wrap that up into this dependencies class that I defined. So it's going to need all the signatures for our dependencies and this fingerprint that represents the state of the code. All right, so back to the signatures method. I did try to squeeze in the type of phase into a live demo, did not manage. So we're going to sub that out with a comment. This is where the typer runs. And once we run, we can generate a signature artifact. And that's just going to need our ID. And it's going to take the fingerprint of all of our dependencies, but it's going to add to it one extra element. And this is a mapping from our own scope ID to our current source version. So everything right now is fully specified in the signatures artifact. And that's the output of the signatures method. Classes is going to be extremely similar, except remember that as well as taking this config, we also now need to take that signature artifact that we just generated in the previous phase. And now we're going to return a different type, a class file artifact. And just as before, we're going to resolve dependencies. And again, remember that although this code, like potentially you may think, well, why not pull out dependencies and call it before and pass it into the signatures and classes? That's true. I've written that version of the code as well. It's less pretty. But also, I'm thinking about each of these methods as a fully encapsulated, referentially transparent component. So I'm just thinking about what does classes need to do? Well, we need to resolve our dependencies. We need to run post typer, and this will use our signature artifact. And then finally, we can generate the class file artifact, which is going to contain our ID. And just as before, we're going to take the fingerprint from our dependencies and just stick one extra entry in there. Which represents our own source version. And that's it. The code, all right, I did stub out the actual compile, but the idea behind this build tool is all here, except that so far, everything is sequential and nothing is cached. So this is slow and it's inefficient. On the other hand, I have written the code how I want to write it. It's clear, hopefully, declarative, functional code. It's expressing a solution to the problem that I'm trying to solve and not how I'm trying to solve it. It's not got any implementation concerns that are leaking through and polluting my type system. Nothing here is wrapped in a future to achieve asynchronous execution. There's no cache. But code like this just is not going to fly at scale. It very quickly becomes a bottleneck. But I did take great care to write referentially transparent functions, which means that now I can make that guarantee to Optimus. And I can do that by adding @node to all of these methods. And now I'm guaranteeing to the compiler and to the Optimus runtime that these are referentially transparent, and I'm going to leave the execution of this to you, which means that now we achieve asynchronous execution, which gives us pipelining, and caching, which means that we don't resolve the dependencies for infra 6 times or however like this compute graph expands to. And I am going to show you how this runs, but first I just wanted to show you a visual representation of what this code will look like. So let's say that I'm going to try from this example that you cannot read. Let's say I'm going to build app, which is the one at the top, and it depends on model and data, which are the left and the right. They depend on infra, which is at the bottom. So I'm going to build app and I'm going to build model. So there are overlapping dependencies here. And if I just draw out, okay, for the sake of the slides, I'm going to abbreviate this. You still can't see it, so it doesn't matter. But now there are letters on each one. Okay, but this is my fully expanded compute graph. So once you've done all the recursion, you eventually stop recursing when you reach infra, because infra has no more dependencies that we need to resolve. I've color-coded the boxes, which you forget the slides. There's a lot of duplication here. And the color coding attempts to show you where the duplication is. So we do have 6 calls to signatures for infra and also 6 calls to dependencies for infra. So if I just expand out this compute graph and I really execute everything naively, this is just not performant code. This is absolutely not the build tool that we want to write. And although in theory I had the pipelining, I kind of enabled pipelining by splitting up the compile into 2 phases, I actually don't achieve anything in practice until I add asynchronous execution. But Optimus is smarter than this, so let's show you what it does. So build scopes will kick off that compile method that we just wrote for model and for app. Then on the top branch, to compile the model, you need the signatures. So this expansion here is just going to show you the tasks that the scheduler can schedule. So for example, compile for the model needs to kick off both the signatures and the classes phase for that scope. But it cannot kick off classes until we have a result for signatures. So this is a visualization. Oh, it's so sad that I spend so much time in my life animating this stupid thing and you can't see it. Anyway, this shows you the full expansion. And now as tasks start completing, hey, this is actually better. As tasks start completing, you will see what they are. So pink means it's running, green means it's done, and we can return that result to our caller. This continues up this recursion. And you can see here on the top branch, now that I've completed the signatures for the model, I can now kick off the classes method. And I've got this little cloud here that just represents the duplicative branch because the slide was just too much. And I got sick of animating PowerPoint. So once we have the classes for the model, we can be done compiling. But here on the bottom branch, we had more dependencies because app depended on both model and data directly, and it then obviously depended on infra. So once these complete, the classes phase can kick off for the app, and then that completes the compilation of the app, and that fully completes build scopes. But this is still not the full picture. And if you could see the slides, you would notice that this branch here, where we're resolving the signatures for the model, is obviously something that we already have an answer for because we were compiling both the model and the app together. So app doesn't need to recompute the signatures for the model. We've got that, and we replace that with a cached result. And it's safe to do that because all of my functions were referentially transparent. I know that the state of the source code hasn't changed, and so I can reuse what I had in cache. And similarly here, we've got the duplication at the bottom there of the signatures for infra. We already computed those because both model and data depended on them. So at some point we had a result, we stuck it in cache, and we just come back, or the scheduler looks up in cache for that exact same input. And if it finds a match, we can safely return the output from cache. So now this looks much smaller than the compute graph that I showed you initially. And if I invalidate one of my sources, so let's say that I invalidate data, and you will recall that app depends on data and model, which then depend on infra. I don't need to invalidate infra, and I don't need to invalidate model, because they have no relationship to data. I do need to recompute data itself, or rebuild data itself, and rebuild the app. And that means that this blue branch now is the branch that I need to recompute. So I haven't invalidated my entire dependency graph, the entire compute. I can take back most results from cache. So let me show you now how this actually runs. I'm going to comment that out. I do have a fuller version of this demo, which is essentially the same code. Let me make this a bit bigger so that you know I'm not lying. Hopefully that's big enough. The core logic here is almost identical. It is identical to what I showed you. The difference is that I've added a ton of logging. And I've also done some setup down here that sets up the dependencies. So now you will get to see what you did not get to see on the slide, which is that infra has no dependencies. Data depends on infra, model depends on infra, and the app depends on the data and the model. So that's the dependency structure. I've set up my build tool so that it's going to build the model and the app. And I've got an external thing here that's going to simulate just bumping up the source version of my data scope. So that's going to simulate data classes and source files changing. And that means that we're going to need to redo the build for data and its dependent scopes. All right, so let me show you how this runs. And you may notice here that this is using OBT to build that code. And let's make this bigger so that, oh, maybe not that big. All right. So what happens here is that we're building these scopes that I promised you, model and app. And you can see that immediately at the exact same instant, two different worker threads have picked up the compile method for scope and for app. And that's because I added @node to my compile method because it's referentially transparent. I didn't have to wrap my return types in futures. I didn't have to set up a thread pool. I didn't have to do asynchronous execution myself. Optimus takes care of that for me. So we kick off both of these, we expand our compute graph, eventually the scheduler reaches a task that it can run and complete, and at any point where the scheduler reaches a point where it needs some dependency, the thread suspends and we can pick up another task on our queue. So it's extremely efficient computation. But eventually we get to the point where we can actually complete the signatures for infra, because that's at the end, that's the very leaf node of our compute graph. And as soon as we've done that, you'll see these two lines here. We're starting now signatures for both the model and the data scopes, and they're also starting on two different threads. So as soon as we have those infra signatures, we can kick off the compiles for the signatures for data and for model. And once those signatures start to come back, we can start to compute signatures for the app, which depends on both of those. And then we'll obviously we wanted to build, remember, the model and the app, so we need the actual classes for those. So we'll start those phases. And then once we're done compiling both of those scopes, once we're done with the signatures and the classes, we get this build output here. And the build output you can see is exactly two artifacts, one for the model, one for the app. And each artifact contains this information, this fingerprint, about what went into it. So if I now simulate bumping up the version of my data scope, so this is simulating some code change. Now, obviously, I do need to rebuild. My root node needs to be recomputed. It can't be retrieved from cache because my dependencies have changed. But you can see that although I start compiling the app scope, I don't even kick off a compilation. There's no log line there for model, and that's because my result for the model scope came directly from cache. Its dependencies haven't changed, so it's safe to reuse it. But again, I can start signatures for data. I don't need to recompute infra. Infra is also still valid. It hasn't changed because it doesn't have a dependency on data, so we pull that out of cache. Then I can recompute my signatures and classes for the app, and you'll see here that now my build result has the exact same class file artifact as before for model. That just came directly out of cache. And this second one has changed because now my data scope has version 2. And as this continues, you can see that this continues to just retrieve results from cache and only recompute the parts of the core graph that it needs to recompute. So I got to write the code that I wanted to write. I got to solve this problem of how do we write a build tool that can achieve pipelining, but Optimus took care of the execution for me. And Adam is now going to show you the real thing, because this alone does not get you to 21 million lines in under 2 minutes.
Yes. Okay.
Okay, so
The thing that Gjeta didn't show is additionally, so in process, we get a lot of caching, but we've got, if you recall from the earlier slide, 150 PRs a day going into a shared integration branch, which is a lot of builds across all the developers to both do the work to create those PRs and then to validate the PRs and then eventually release that. And without sharing the artifacts that we produce, we repeat a lot of the work across all of those builds. So we'd like to have distributed caching. Given that we have the inputs captured as a fingerprint, we can use that as a key for the cache to then store the artifacts and look in process for them if the process has been up or on the local file system And lastly, in the remote cache that's shared and populated by all these different builds. And lastly, if we don't find it any of the places, do the compilation. So I can show this on our actual code running. Hopefully that's big enough. Should make it bigger. Can people see? Okay, so what I've done to prepare is we ran OBT in an interactive mode, and I did an initial build of all of the artifacts on a commit from last Thursday. And it took about a minute to pull all the artifacts out of cache and install them in my local workspace. Now that the process is still up, if I ask it to update, it takes just a couple of seconds, and it has determined that 28,000 or so artifacts are up to date, and it didn't need to install any new ones. Now I can switch. And so we're on a branch called demo1, which is pointing at that commit from last week. If I say want to pull upstream changes from yesterday, about 3,000 files have changed in that time period, with a number of changes all throughout the code base. Most of the dependency graph will be invalidated, and I can switch back and ask OBT to update my build artifacts with oh wait. We actually need to switch the branch. But it only took 4 seconds. I didn't lose a lot of time. So now this should take longer because we'll need to actually move some files around from cache, from local file system, and from the remote. You can see here it scanned the file system, saw 200 or so directories had changed. That took a few hundred milliseconds, and now we are doing the build. On the left here, you can see some gibberish in the brackets. That is the real scopes with different names for the purposes of the demo to protect innocent scopes. But it is the real project. I guess you'll have to trust me. So as this goes, this is a pretty important part of the workflow as we rebase our changes on top of it. Obviously, I don't have any changes locally here, but if I did, it would just be the portion of the dependency graph on top of this set of cache hits that's running that I would need to build on top of it. And so as Gjeta showed during her demo, that few lines, 100 lines of code took only a couple of seconds to build. So now this is finished. It took, again, about a minute, and I can continue working iteratively, and I've updated the branch I'm working on. Okay, so again, the version of OBT that Gjeta just built is very simplified. Obviously, it didn't even do compilation. In the real world, OBT does more than just orchestrate the pipeline compilation. We produce a bunch of different artifacts, primarily to be able to run the code, like application scripts and Docker images. We have integrated with IntelliJ, as you saw during Gjeta's demo, with the build server protocol, and OBT acts therefore as the authoritative source of truth for the project structure and the external dependencies. And last thing to mention is that when we do have to do the compilation, we can also try to do an incremental build from shared zinc analysis artifacts and do an incremental compilation using that. So at the time that we made the switch from our prior build tool to OBT, we were able to do a kind of an apples-to-apples comparison, build performance, the same number of lines of code. At this point in time, in early 2020, probably had half the number of lines of code, so from 21, call it 11, 12 million lines of code, for a core library change that invalidates most of the dependency graph. We saw a pretty substantial decrease in build time. That's primarily due to pipelining. And then for changes in leaf projects that don't invalidate much of the computation graph, we benefit from both caching and pipelining and have a pretty dramatic benefit on the order of a couple of minutes. So with the Optimus platform, we're able to write, as Gjeta says, the code she wants to write that just express the problem domain using referential transparency. And at node, we get the parallel execution and caching. And we have been able to use that to build a build tool that enables our developers on the platform to be productive on a code base that is 21 million lines of code. We are open sourcing OBT and the Optimus platform. Some of the code is pushed already, including the demo code that Gjeta wrote. It's under the Morgan Stanley organization in GitHub, under the Optimus Cirrus project. The last thing to acknowledge is that there's a lot of people working on Optimus and OBT, and this presentation and the platform and the build tool would all not be possible with them. And there's way too many people to mention in this talk, but it's important to acknowledge. And I think that's it. Are there any questions?